The term malleable means to be able to change something's physical shape. Okay, so imagine like a hot piece of iron coming out of a forge, and they're going to make like hammers and nails out of it and things like that. And when they hit it with the hammer, it changes shape, right? But the iron, if it's still hot especially, won't break. Okay, it won't just snap in half. You can imagine another example would be like bending a paperclip, right? It's made out of metal, right? So ionic compounds tend to be brittle, right? And as a matter of fact, molecular compounds also tend to be brittle things. In other words, if you hit it, if you try to change its shape, it's just going to break. Okay? Metals, on the other hand, are malleable. You can change their shape. You can alter them. They're also referred to as ductile, which means that you can make wires. You can stretch metals and make wires. Okay? So, of these compounds right here, let's go ahead and zoom in. This one's ionic. This one's a gas. Water can be liquid or gas. I guess, or solid. Okay? But imagine what happens if you hit a piece of ice with a hammer and it just shatters. It just breaks into a bunch of pieces. This is gold. And then carbon is diamond. Okay? So of these 5 choices, the only one that's a metal is the gold. And thankfully, gold is malleable because then we can make all kinds of wonderful jewelry out of it and electronics. Right? Phosphorus pentachloride. Hopefully, you all have your nomenclature right at the top of your brains, and you read the words phosphorus pentachloride, and almost a knee-jerk reaction, you write this. Okay, as the formula for phosphorus pentachloride. So we're not really going to talk about polymers, not very much anyway. A lot of things are made of polymers, but we're not going to get into them as far as bonding, and there won't be any questions on your exam about it. But looking at this phosphorus pentachloride formula, this has only nonmetals. The only way that it can be anything other than the covalent is if it had metals there, right? So a metallic compound, there's no metals there. There's no metals in order to make it an ionic compound, which means that it has to be polar covalent. Not polar, but just covalent, sorry. Okay. Polyvinyl chloride is a plastic. So do plastics fall into any of the other categories? So plastics are not metals, so we can't have a metallic compound. Polyvinyl chloride, yeah, it might have some nonmetals in it, but it definitely doesn't have any metals, so we're going to count out ionic. And I'm going to tell you right now it's not covalent, so this is an example of a polymer. Okay? And like I said, this is not an issue that you really need to worry about, but it is in the slides, so we're going to talk about it anyway. Solid carbon dioxide, also called dry ice, has a formula that looks like this one. So are there any metals? The answer is no, so we can count out the first 2. Now the next question, molecular covalent or network covalent? Network covalent must be only one nonmetal. Okay? Here we have 2 different nonmetals. So it's a molecular covalent solid. Potassium permanganate. Are there metals? Yes. So right away we can count out anything that's covalent in our choices. Okay. Now the metallic compound, remember the metallic compound, only one. Okay. So we've got two different metals in there, potassium and manganese. Right? So this one does not count for metallic. So we're going to go with an ionic compound. Diamond. Pure diamond is pure carbon. Right? So pure carbon is not a metal, so we can immediately count out these two choices. The network covalent, we just talked about this about 2 slides ago. The network covalent is the one where it's only one non-metal. There's your answer. So as we're going through, I already mentioned when we approach a question, one of these numbered slides, I encourage you to pause and work on the problem and then come back and go through the example with me. I also encourage you to pause me regularly or replay things that I say, because I'm not exactly writing down every single word that's coming out of my mouth. Okay? Now, you can do closed captioning on YouTube, which is handy sometimes. So our next topic is intermolecular forces. So intermolecular is different from intramolecular. Intramolecular is the interaction inside molecules. So that's the interaction between individual bonds. Okay, and that's sort of what we've been talking about so far. We've been looking at these bonds that are inside these water molecules, right? And how things go together. But intermolecular forces, we are focused on what's happening in between molecules. Okay? And these are interactions. And this is a very important idea. Interactions, not physical bonds. Okay? So these molecules are, it's almost like they're sticking to each other, okay, instead of actually being bound to each other, right? And in the case of solids, those interactions are very strong, and they're strong enough that they are effectively stuck in place. But intermolecular forces are not physical bonds, they're just interactions between molecules, okay? So if I rank these 3 different forces in terms of strength, with 1 being the weakest and 3 being the strongest, I'm going to put a ranking of 1 with London dispersion, a 2 with dipole-dipole, and a 3 with hydrogen bonding. Okay, so let's get in here and start talking about how these individual forces work. Right? So we're going to start with the weakest one. We're going to start with the London dispersion. Okay? And London dispersion is kind of the proper name. Okay? So just for short, we will often just say dispersion. Okay? So London dispersion forces are momentary shifts in the electron cloud. Of a molecule. Okay? So what does that mean? So far we've been, talking about molecules in terms of sort of very rigid shapes, right? The reality is that most molecules have a cloud of electrons around them. Okay, and in the center you have the nuclei of the molecule. So if I've got an electron cloud, it's full of negative charge, right? And let's say I have another electron cloud that is also full of negative charge. These are the electrons, right? So what can happen is those electrons are in constant motion, okay? So at any given moment, I might have my electron cloud with most of the electrons over on one side. And let's say the other electron cloud nearby also has most of its electrons all on one side. So what this does is just for a moment, I've got a negative side to my molecule and a positive side to my molecule because my electrons are negatively charged. So if they're all to the left, then I've got a negative charge on the left and a positive charge on the right. So let's say this molecule has the same scenario going on. Okay? So guess what? Positives and negatives attract each other, right? So just for a moment, I have an interaction. Right? Between that positive and that negative. But it's momentary because everything is in constant motion. So in the next instant, those electrons shift around and suddenly there's no more attraction. Okay? The cool thing about dispersion forces is that everything can do this. Okay? All molecules have an electron cloud, and that's all you need in order to do dispersion forces. So when you're deciding what forces a particular molecule has, dispersion forces is always going to be one of your answers. Okay? So, but because this is a momentary interaction, that means this is also a weak interaction. Okay? So, just like in class, I'm going to take a moment and erase. And we're going to talk about our next type of interaction.